All right, 3.3, we're doing all the derivatives for the trig functions. We'll look at these special limits that we used for the proofs of sine and cosines, derivatives, right? We did that in 2.8, and we'll look at those graphs again here briefly just because they're still in the notes. But we'll get some practice with the product and quotient rules and really just looking at those derivatives for our 6 trig functions. So 3 special limits. The limit as x approaches 0 of sine x over x is 1. That could also be seen upside down, right? Limit as x approaches 0 of x over sine x, right? Really, if you take a reciprocal, it's 1 over that thing. So if it's 1 over 1, it's still going to be 1. Likewise, for our second limit as x approaches 0 of 1 minus cosine x over x, if you did factor out a -1 or something, we could also write this as the limit as x approaches 0 of cosine x minus 1 over x equals 0. And again, if we did factor out a -1 from the numerator, -1 times 0 would still be 0, so we can use it both ways. And then the one for e is here. We don't really use it in the class, but more to see where the definition of e comes from. So the limit as x approaches 0 of 1 plus x to the 1 over x power is where we get e. And the box here is sort of important because your whole goal of evaluating these limits is just to manipulate to make the argument inside the trig function and the value in the denominator match. So as long as these boxes have the same value, we make use of the properties, right? That x can represent anything as long as that same anything is in the denominator here. So to find the following limits, we don't have the boxes matching here or the argument matching the denominator. We've got a 3x and just an x. So we need to introduce a factor of 3 to make that denominator match what's in the argument. All right, so we can rewrite this a couple different ways. You could factor the 3 all the way out or pull it all the way out front using those limit properties if you want. But biggest thing is just to remember that when you're multiplying by a 3, by a trig function, it does not affect the argument. So the 3 would still be out front. And then we've got a 3x in the argument now, a 3x in the denominator. So the fact that these two things match means we can take advantage of that first special limit. Limit as x approaches 0 of sine x over x is 1. So we end up with a 3 times 1, or 3 for our limit. And the rest will work pretty much the same way. So you can try them or you can watch, but I'll run through them all. So here we've got one that looks almost exactly like our second limit, but we've got a 7x in the argument and just an x in the denominator. So we need to introduce a factor of 7 to make the denominator match what's in the argument of cosine. So we've got limit as x approaches 0, 1 minus cosine x over x, and we're going to multiply by 7 over 7. Right, we're working with fractions, so we've got to multiply by the same value in the numerator and denominator to keep that equivalent fraction, right? We're multiplying by 1 every single time. And for this one, I'll keep that 7 all the way out in front of the limit from the numerator. So we can see just the form we want inside the limit here. So we've got the limit as x approaches 0, 1 minus cosine 7x, all over 7x. We can see again the argument matches what's in the denominator. And so we end up here with our 7 times our limit as x approaches 0 of 1 minus cosine 7x over 7x is 0. And 7 times 0 gives us 0. All right, for 3, same sort of thing will work out for tangent, but they're going to want you to divide it into pieces just to see what's going on. So we can rewrite this one first using some trig identities as the limit as x approaches 0 of sine 2x divided by cosine 2x all over x. And dividing by that x, if it helps, you can think of it as multiplying by 1 over x, but we'll end up with a sine 2x divided by x times cosine 2x. All right, and then to make it match, so we can get rid of some pieces that are causing the problems, right? Sine of 0 over 0 times cosine of 0 would be 1, gives us that 0 over 0 indeterminate form. So we're still working on these ways to get rid of it and get to a limit we can actually evaluate. So sine 2x over x cosine 2x. I guess I didn't have to rewrite it this time because it wasn't after the equals just getting in the way, but we'll multiply by 2 over 2 to get that 2x in the argument for sine, matching a 2x factor in the denominator. All right, so this one's going to become the limit as x approaches 0. We're going to have sine of 2x over 2x cosine 2x. And that other 2 we can leave in the numerator or pull all the way out front. But I'll put it there for this step, and then we'll write it out the way we'll evaluate. So that 2 can come out front. And then we've got the limit as x approaches 0 of sine 2x over 2x times the limit as x approaches 0. We'd get a 1 over cosine 2x, right, if we split that into a product. And limit law applies here because both of these limits do exist, so we can break it up into these two pieces. And when we do the multiplication, we get a 2 for our sine 2x over 2x. As x goes to 0, we get a 1. And then our limit for 1 over cosine 2x as x goes to 0. Cosine of 0 is 1, so that gives us a 1 over 1, or another 1, so it should give us a 2. And then for the last one, we've got to manipulate a little bit more to make everything match. We've got a sign in the numerator and a sign in the denominator. So we've got the limit as x approaches 0 of sine 3x over sine 2x, which if we sub in 0 would give us a 0 over 0, or that indeterminate form again. So we need to multiply by or bring in a 3x in the denominator, right, to match the 3x in the numerator. We also need a 2x in the numerator to match the 2x in the argument for that sign in the denominator. So what we need to multiply by is a 3 over 3, right, for that 3 in the argument of the numerator, 2 over 2 for the 2 in the argument of the denominator. And the mistake a lot of people make is to multiply by x squared or something. But really just x over x. We'll introduce an x into the numerator and an x into the denominator to give us both of those special limits to match both of those arguments. So we can rewrite this one. The 3 in the numerator is the extra. We can pull that out front. The 2 in the denominator is the extra. We can pull that out front. And then we got our limit as x approaches 0 of a 2x sine 3x over 3x sine 2x. All right, and then we can see that 3x over 3x is there. We've also got a 2x over the sine 2x. And again, we looked at, or we talked about how that limit works both ways, right? The 2x on top, sine 2x on the bottom, or sine 3x on top, 3x on the bottom. So we can split it into pieces. You don't have to. You can see both of those would go to 1, but we can write it out as a limit as x approaches 0, 2x over sine 2x times limit as x approaches 0 of sine 3x over 3x. And again, we're using those special limits. We can see the sine 2x argument matches that 2x in the numerator. And then the sine 3x, that argument matches the 3x in the denominator. So both of those will go to 1. So we'll have a 3/2 times 1 times 1, or 3/2 for our limit. All right, so there'll be some more practice with those in the homework, but very, very similar. You're just multiplying by 1 to introduce whatever factors you need. All right, and then, so we're looking here at a graph of f of x, and we want to sketch f prime of x and then f double prime of x. And if you did see this in class, then you already did it, and you can maybe skip it if you want. But the big idea, again, wherever we have these horizontal tangents, right, that means our derivative is 0. So that would correspond to a 0 on our derivative function. So at negative 3 pi over 2, pi over 2, negative pi over 2, pi over 2 as well, and then 3 pi over 2. We've got those horizontal tangents, so the slope is 0, or the value of the derivative is 0. So f prime of those values would be 0, right? So we have our x-intercepts for our derivative function. And then beyond that, for the sketching, we were looking at, a positive slope for the tangent line, leading to a positive value for the derivative, a negative slope for the tangent line, leading to a negative value for the derivative. And maybe we can use some color for that. So positive going up, and then negative sloping down. Right, and we can use that to help us graph the function. Right, we can find maybe the place where we have the highest slopes and smallest slopes and kind of go from there. And if you did see when we're working with the worksheet in class, or if you want to try it on your own, here, I've never clicked on ruler. Let's see what happens. All right, I've got a ruler. I don't think that's going to help much, but hopefully we can see that's, we'd need a different scale to see a 1-to-1. All right, get out of here, ruler. But the idea, again, if we do look at some different slope lines here, right, we're getting steeper, right? We're going up, increasing towards, right here is going to be a slope of about 1. And then as we move up towards pi over 2, you can see that slope start to decrease again, right, or level off towards 1. So where we have our highest positive slope in this piece from minus pi over 2 to pi over 2, we're going to get a slope of about 1. Right? But we know everywhere in there we've got a positive value for our derivative, right? Because all those little red pieces would have positive values or positive slopes. So our slope is increasing to like a max of 1, and then it starts decreasing back to that next horizontal tangent at 0. And then we can draw the next piece in blue. We can see the same thing. We're close to 0 up here, and then it starts getting steeper and steeper, down to a slope of about -1 at pi. And then eventually, as we move closer to that next horizontal tangent, our derivative is getting closer to 0 again. So we're negative, right? Negative slopes for all those blue lines. And we get more and more negative until we get to about -1 at pi, and then are getting closer and closer to 0 again, so less negative towards 3 pi over 2. We can see the same pattern going between -3 pi over 2 and -pi over 2. So we have another piece over here. All right, and then some positive ones before that, if we're going all the way back. And so if you do remember your trig, then you should see, hopefully, that this first graph follows what we'd call sine x, right? And its derivative here, f prime of x, looks a whole lot like cosine x. All right, and when we do the second derivative graph, or the derivative of this first derivative, we'll find out the derivative of cosine, essentially. Right, so we want to look first, always line up those horizontal tangents, right, for our zeros of our derivative function. So we've got zeros at pi, -pi, 0, and pi. And then, similar to what we did for the last one, we can see all these positive values, right, positive slopes going from -pi, right, getting steeper and steeper until we get to -pi over 2, and then to start leveling off again towards that next 0. So more positive to less positive, right? We're getting bigger as we approach -pi over 2, close to that value of 1, and then less positive as we go down towards 0. All right, and then between 0 and pi, all right, we'll get these ones that are getting steeper and steeper negative, going to a -1 as our min, and then starting to level off more. All right, so less negative as we move towards pi. So down to pi over 2, and then coming back up to pi. And you can see the same thing, right? Those patterns repeat for our other two sections. And although I don't know if I put enough curve on there, hopefully you can see we've got that sort of sine curve again starting at 0. But if we start from 0 and take our period to 2 pi, we're going down first, right? -1 at pi over 2. So this should be your graph of, we'll call it f double prime of x is minus sine x. Right, but that's also telling us the derivative of cosine x should be minus sine x. And if you did want to try one more time, maybe 2 more times, you can complete the whole cycle. Our derivative of negative sine x would be negative cosine x, and then negative cosine x, which introduces the negative like we see here, would get us back to sine x. So you're welcome to try more if you want to practice the graphs, but we'll go through the derivatives. And they're all listed here for your convenience. Our derivative sine x is cosine x is minus sine x. We can kind of see from the graphs. We also did the proofs of them in class a couple weeks ago. So we'll look at tangent or cosecant or something. Let's do one of those proofs just to practice quotient rule, because really that's what we're doing. And so that's how you'd prove the other 4 derivatives. Once you know sine and cosine, because all the other trig functions can be expressed in terms of sine and cosine, you can just use quotient rule to do the proofs. You don't need to go back into those special limits or anything. So for our first one, let's say we want to do the derivative of tan x. Probably the only one I'll do. You can try the other ones if you want, but this would be the same as the derivative of, right, tangent x is equal to sine x over cosine x. Which is going to give us a quotient rule. So I'll write it out once in here with f and g, and then we'll move to maybe the prime notation that you'll get used to for the rest of the problems. But in terms of what we did for working class, that was our f of x, right? Our denominator function was our g of x. And then we did our scratch to find the derivatives of each piece. Right, so f prime of x, derivative of sine x is just cosine x, and g prime of x, our derivative of cosine x was minus sine x. Right, we just looked at it with the graph, so it's right in the box above there. And then when we do our derivative, we're going to get an f prime of x, g of x minus f of x times g prime of x all over g of x quantity squared, and then fill in everything. So f prime is a cosine x, g of x is also cosine x, minus f of x is sine x, and g prime of x is a minus sine x, all over g of x would be cosine x quantity squared. All right, and then our numerator will end up with a cosine squared x plus sine squared x, right, from that double negative, and then a cosine squared x in the denominator, which will give us a 1 over cosine squared x. And with our reciprocal identity, that is secant squared x. All right, so we got our derivative for tangent is secant squared x. You can do the same sort of proof. It's good practice for quotient rule and getting used to derivatives for sines and cosines for your derivative of cosecant, right, which will give you minus cosecant x cotangent x. Your derivative of secant x with respect to x, secant x tangent x, and your derivative with respect to x of cotangent x, which would just be minus cosecant x. So good practice to try the other three, but they'll all work the same way. Okay, we've got a few more just to practice with these new rules and practice our product and quotient rules as we go, and really just to help refresh some trig. So we're finding the derivatives here. We've got f of x equals 1 minus sine x over cosine x. If you want to rewrite it as h and use f and g, that's fine. I'm going to try and write it out the way most people tend to as they practice and get used to this. So instead of labeling and doing a whole bunch of scratch work, we'd call f prime of x here, right? We want the derivative of the first function, so we just use the prime notation to say we need the derivative of that. That's like writing f prime of x, right? And then times cosine x minus 1 minus sine x times the derivative of cosine x all over cosine x squared. All right, so we introduce the prime notation to get the derivative of the top function times the bottom minus top function times derivative of the bottom all over that bottom function squared. And then we can work through. So derivative of 1, the constant is just 0. Our derivative of sine x would be cosine x. We've got the minus in front, so a minus cosine x times cosine x minus the 1 minus sine x is going to stay. Our derivative of cosine x is minus sine x all over cosine squared x. And then we get a minus cosine squared x. And let's see, we'll keep the minus here and do the distribution for the sine x in there first, or minus sine x. So we get a minus sine x and then a plus sine squared x when we distribute, right, into those two terms, all over our cosine squared x. And then that leaves us with a minus cosine squared x minus sine squared x, just so we can see them together. Right, I did this one first, and then the plus sine x all over cosine squared x. And if we do want to simplify that at least, a tiny bit, so we can do the extra trig I had planned here, we can probably take up a little more room here because the other derivative should be quicker, right? There's no quotient rule over there. But we can rewrite this as a negative 1, right, times cosine squared x plus sine squared x. And then plus sine x over cosine squared x, which is a negative 1 times 1, so just negative 1 plus sine x over cosine squared x. All right, and we simplified that one as much as we can just to hopefully help with this next part, right, where we practice with our trig identities and get used to some trig again, so you hopefully remember it for Calc 2 where you really need it. But that's our first derivative. And then for b of x, a little bit more straightforward, or sorry, not b of x, part b, f prime of x, our derivative of secant x is just secant x tangent x, and then minus our derivative of tangent is just secant squared x, right? Again, you can see them both, right? They're right up there if you got to look up for a while. They are things you'll have to memorize or do a lot of extra quotient rules on the test. As long as you remember sine and cosine, you can get these, but you definitely don't want to waste that much time. All right, and then to show the functions are the same and that the derivatives are the same, you can go about it in a couple different ways, right? Work from the left side, work from the right side. Maybe I'll leave those for you. It's trig. Try the trig. Ask me questions if you need to. But multiplying by the conjugate is a really good option. Run through your Pythagorean identities if you need to, stuff like that. So try them out. Ask questions again if you need to, but we'll practice a few more derivatives for the video here. So we've got another quotient rule here, 1 minus cosine x over sine x. So for f prime of x, we want again the derivative of the top function, so 1 minus cosine x prime times the bottom function, so times sine x, minus our top function, 1 minus cosine x, times the derivative of sine x, our bottom function, all over bottom function squared, so sine of x quantity squared. And then as we start running through, our derivative of cosine was minus sine, derivative of 0 was 0, so the minus negative sine x just gives us sine x times sine x, and then minus the 1 minus cosine x stays here, derivative of sine x is just cosine x, and our denominator is just sine squared x. All right, so if we rewrite a little bit in the numerator, we get a sine squared x. We'll keep that minus, do it for the next step. So we're distributing in the cosine x here. So we get a cosine x minus cosine squared x all over sine squared x. And that'll give us our sine squared x. Now if we do that second distribution, minus cosine x. I should have probably wrote the other order again, but we'll just do plus cosine squared x and put them together later, or just hopefully recognize that identity, but equal to sine squared x. And so definitely want to simplify this if you can, right? The sine squared x plus cosine squared x should give us 1. So our derivative here would be 1 minus cosine x over sine squared x. And you could keep manipulating the trig function forever and ever and ever, but we'll stop there. Hopefully that's good enough to see. And for b, we've got a little product for our first term, 2x cosine x, and then minus sine x for our function. So we'll do the same thing, writing out the product rule, maybe with just that prime notation instead of the ddx's, and rewriting with a couple different function names all over the place. And we'll just write f prime of x here is equal to, so for this product, right, we need our product rule. So that was the derivative of the first function, so 2x prime, times the second function, cosine x, plus first function 2x times the derivative of the second function, cosine x. And then if you don't want to, I guess, confuse yourself and say, did I take the derivative of the second term, the sine x, or not yet? You can just write it as a minus 2 and then keep that prime notation to say I still need to take the derivative of sine x as well. If you want to do it in that first step, completely fine. But our derivative of 2x, just 2, right? The constant stays, the derivative of x is just 1. So we get a 2 cosine x for our first term. And then the 2x stays. Our derivative of cosine x would be a minus sine x. And then we get a negative 2. Derivative of sine x is cosine x. And so we can see, hopefully, some simplification at the same time. The 2 cosine x and minus 2 cosine x will go to 0. So we'll just be left with a minus 2x sine x for our derivative. All right, and the last one brings in a quotient rule again and makes us make some connections to what we know about the derivative. So we want to find the derivative and use it to determine at which values of x the graph of f has a horizontal tangent. Right, so the connection you want to make, that horizontal tangent, means f prime of x is 0, right? The slope is 0, or the derivative would have a value of 0. So once we find our derivative, we'll find out where it's 0 to answer that question, where our original function has a horizontal tangent. So f prime of x is equal to the derivative of secant x times 1 plus tan x minus secant x times 1 plus tan x is derivative, right? All over 1 plus tan x quantity squared. Derivative of secant x goes to secant x tangent x, then times 1 plus tangent x, minus secant x. Derivative of 1 would be 0, derivative of tangent x, so we're multiplying by a secant squared x, all over our 1 plus tan x quantity squared. Will kind of drag with us the whole way. So distributing secant x tangent x into the 1 plus tangent x, we get a secant x tangent x plus a secant x tangent squared x, and then minus a secant cubed x, all over that 1 plus tan x quantity squared. And it might take some manipulation to find the right factorization here, but for the second two terms, if we see like a tan squared, secant squared, cosine squared, sine squared anywhere, we can usually draw from those Pythagorean identities. So if we factor out a secant x from those second two terms, we're left with a tan squared x minus secant squared x, which if you manipulate your Pythagorean identity with tangent and secant, is going to give you a -1. And that whole thing, right, and before we do that, still over 1 plus tan x quantity squared, which would then give us a secant x, tangent x, let's do this way, minus secant x, right, because secant x times -1, all over our 1 plus tan x quantity squared, and we can factor out a secant then. So we get secant x times tan x minus 1, all over 1 plus tan x quantity squared. All right, and then if that's our derivative, we're kind of connecting back to the top and saying, all right, we want to know when f prime of x is equal to 0. So if f prime of x is that secant x times tan x minus 1 all over 1 plus tan x quantity squared. Right, we're just looking for, when we're working with a fraction, rational function, the numerator to equal 0, for the function to be 0. So we've got secant x equals 0, or tan x minus 1 equals 0. And secant x can't equal 0. 0 is not in the range of secant. So really we're left with when tangent of x is equal to 1. And 1 and minus 1 will come at those multiples of pi over 4. Positive in quadrant 1 and 3, so x would have to be pi over 4 plus, I guess n pi would work, right? 1 pi, 2 pi, 3 pi, that'd get us halfway around the circle each time, and where then n is an integer. All right, so those quadrant 1 and 3 multiples of pi over 4 will give us a positive 1 for tangent, which makes our derivative 0, which means we've got a horizontal tangent on our original function. All right, so practice some of those, and then we'll do 3-4 together in class next week.